This is number 52 from section 3, chapter 6. It reads, the combustion reactions involve reacting a substance with oxygen. When compounds containing carbon and hydrogen are combusted, carbon dioxide and water are products. Using the enthalpies of combustion for C4H4, C4H8, and H2, calculate the delta H for the following reaction. Now I have 3 reactions here, and I've taken the liberty of drawing them out and balancing them already. So I have the appropriate stoichiometric coefficients here. And what I want to point out first off is our goal in terms of flipping these equations forward or backwards and having different species cancel out is to create this overall reaction. So for some reason, my eye always goes to the product here, C4H8. This needs to be a final product. The only time I have this represented in the equations I have here is as a reactant in this second reaction. So I know first off I'm going to have to flip this equation to draw the reverse reaction. And as a result, this delta H value is going to have to become a positive. Now, it's kind of difficult to picture this without writing it down, so I do suggest doing these types of problems in pencil so you can move them around quickly and not having to worry about permanent pen marks. So I know I'm going to have to flip this particular equation, so I'll get myself some room here. I go 4 CO2s. Let's see. I'll just skip the phases just for the sake of simplicity. Plus 4 H2Os react to yield 1 C4H8 and 6 O2s. Alright, so this way I have that C4H8 as a product. Now what I need to do is get rid of everything else, because notice there are no other products here. So I have 6O2 on the product side. I need to get rid of that somehow. And if I examine my original 3 equations, I have, as long as I don't flip them, I have 5 O2s and a half O2. So that's not quite going to cancel out my 6 on this side, and I would be able to cancel them out if I was able to have 6 oxygens or O2s on the reactant side, but I don't have 5.5. However, if I go and double the amount of action going on in that reaction, I'll have 2 H2s, 1 entire O2 molecule, and that would give me 6 O2s overall. So there would be 6 O2s on the reactant side, 6 O2s on the product side. I would be able to cancel that out. Be that as it may, notice I'm going to have to double, in addition to the oxygen stoichiometric coefficients for everything in this reaction, as well as this delta H, because I'm doing twice as much stuff, twice as much energy is going to be released. So let's go ahead and write that in. 2H2 plus 1 O2, and that'll be 2 H2Os. Alright, let's see. So I will have gotten rid of the O2s in this way. However, notice that, but now I have this H2O going on here. I have 2 H2Os as a product, 4 H2Os as a reactant. Those would cancel out. However, notice that there are no H2Os in these reactants up here. Yeah, the product H2Os would cancel out, but I'd still have 2 more H2Os on the reactant side. However, notice in this first equation there are 2 more H2Os as products, so I have a total of 4 H2Os as reactants, 4 H2Os as product. Those will cancel out and I will be good to go. Oops. CO2 plus 2 H2Os. All right, let's see here. Now, before I start worrying about my delta H's, which will be what I am trying to accomplish at the end here, I want to make sure that what I want to cancel out will cancel out. Let's see. O2s. There are no O2s present in this final reaction. So I have 6 total O2s on this side, 6 on this side. Use red to cancel them out. Those will cancel out. 4 CO2s on the reactant side, 4 CO2s on the product side. Those will cancel out. Let's see, I have 4 H2Os on this side, 4 H2Os on the product side. Those will cancel out. And I have 3 species that I haven't canceled out yet. I have C4H4, which I need 1 of. I have 2 H2s, which I need 2 of. And then I have 1 C4H8, which is my final reaction. So I have 1 C4H8 plus 2 H2s reacting to yield overall 1 C4. Oh, I'm sorry. This should be a 4. My bad. H8. And now to get the answer that will give us points, calculate delta H for this reaction. Now, what I've done here is I've set up 3 different reactions, intermediate reactions, that will result in the final reaction. I do this because, as per the first law of thermodynamics, in the conservation of energy, these 3 steps together will equal this final overall step. Okay, this is a state function. It's a state function. Doesn't matter how you got there. There is no difference between the sum of the steps and the final product. Let's see. So for now, I didn't do anything to this initial equation, so that delta H will stay the same. I did flip this second equation, so this will become a positive value. I didn't flip this equation, but I did multiply everything in it by 2, so I'll multiply the delta H by 2. Let's see here. I ought to be able to do that in my head, but I don't want to. Let's go negative 286 times 2. So I have negative 572 kJ. Now, in the same way that I kind of summed all of these equations up to yield this final equation, I'm going to do the exact same thing to these delta H's. So I'll go negative 2,341 plus 2,755. That's a positive value. And then plus a negative 572. And overall, this reaction I've indicated here will have a delta H of negative 158 kJ. Now, this isn't per mole. Well, I guess actually it kind of does work out kind of per mole for 2 of these. But this delta H is for the entire equation, everything here. So this would be 158 kJ released per 1 mole of C4H4 used, or 158 kilojoules released per 2 moles of hydrogen used, or 158 kJ released per 1 mole of C4H8 formed. Alright, so that's how I would use that if you needed a molar value. But that's not what we need for this particular question. Ask for the delta H for the entire reaction. And there we go.